If we know the input signal and we know the system, how can we predict the output? Testing every possible signal would be impossible. Fortunately, signals and systems theory provides a powerful mathematical tool that allows us to calculate the output of a system directly. This tool is called convolution, and it forms one of the most important foundations of signal processing and RF engineering. In previous lessons, we learned that an impulse response completely characterizes a linear time-invariant system. We also learned that real-world signals can have infinitely many possible shapes and durations. This creates an important challenge for engineers. Suppose we know the impulse response of a filter or communication channel. We would like to predict how that system responds to any arbitrary input signal. However, directly analyzing every point of the signal separately can quickly become difficult, especially when dealing with complex waveforms. The problem is finding a general method that combines knowledge of the input signal and the system's impulse response to determine the output. This requirement leads directly to the concept of convolution. Convolution is the mathematical operation used to determine the output of a linear time-invariant system when the input signal and the impulse response are known. The key idea is that every complex signal can be viewed as a collection of many tiny impulses. Since we already know how the system responds to a single impulse, we can determine the response to the entire signal by adding together all the shifted and scaled impulse responses. For continuous time systems, convolution is represented mathematically as the combination of the input signal and the impulse response. The result of this operation produces the complete output signal. In signals and systems theory, convolution serves as the bridge between the input and output of an LTI system. Intuitively, convolution can be thought of as the process of accumulating the effects of many small signal contributions. Imagine throwing multiple stones into a pond. Each stone creates ripples, and the final water surface becomes the combination of all those overlapping ripple patterns. Convolution works in a similar way. Physically, consider a communication channel. Every tiny part of the transmitted signal travels through the channel and generates a corresponding response. The received signal is the sum of all these individual responses arriving at different times and amplitudes. Mathematically, convolution involves shifting the impulse response across the input signal, multiplying corresponding values, and summing the results. While the procedure may initially seem complex, its purpose is simple. Calculate how the system transforms the entire input signal based on its impulse response. Convolution appears throughout RF engineering and communication systems. Whenever a signal passes through a filter, amplifier, transmission channel, antenna system, or receiver, convolution provides the mathematical framework for determining the resulting output waveform. In wireless communication, the received signal is often modeled as the convolution of the transmitted signal and the channel impulse response. This allows engineers to analyze multipath propagation, fading effects, and signal distortion caused by the environment. At the system level, convolution supports the design of equalizers, digital filters, communication receivers, radar systems, and signal processing algorithms. Many modern wireless technologies rely on convolution-based models to predict and optimize performance. Convolution is an extremely powerful tool, but it applies directly only to linear time-invariant systems. If a system is nonlinear or time-varying, convolution alone may not accurately describe its behavior. Additional modeling techniques become necessary in those situations. A common mistake is viewing convolution as merely a mathematical formula to memorize. In reality, convolution represents a physical process that describes how systems accumulate and combine signal effects over time. Understanding the underlying intuition is often more important than remembering the equation itself. The concept of convolution naturally leads to one of the most important ideas in signal processing, the relationship between the time domain and the frequency domain. In the next lesson, we will see how convolution in the time domain becomes multiplication in the frequency domain, dramatically simplifying system analysis. In this lesson, we learned that convolution is the mathematical operation used to calculate the output of a linear time-invariant system from its input signal and impulse response. We also saw how convolution provides a practical way to predict system behavior without analyzing every possible signal individually. In the next lesson, we will explore time versus frequency domain and discover how signals can be viewed from two different but equally powerful perspectives. If you found this useful, like the video, subscribe, and follow for the next lesson.